It is a section 6.5, least squares problems. In this section, we'll try to find a best solution for linear systems. A is an m by n metric, then ax equals b may have no solution, particularly when m is larger than n. In real world, m is much larger than n. M represents the number of data points, and n denotes the dimension of the points. So we'll try to find a best solution rather than the exact solution. Let's begin with a definition. A is an m by n metric. B is in Rm. A least squares solution of the linear system Ax equals b is a vector x hat in Rn such that the norm of b minus ax is minimized with x hat. The norm is L2 norm, so each component will be squared and summed, so that that is that's reason we use a square. So least square solution of the system. The information metric A and the observation vector B are often obtained from a certain data set. Finding a best approximation or representation is a major subject in research level. Let's see this data set. There are blue dots and red dots. Red dots are noise. Once we are using all points, then we can get such a line. This is the best line. And however, we can eliminate the red dots and use only the blue dots, and then we can find the blue line. By using all the points, the algorithm, so-called the RANSAC, the random sample consensus, that can find this cyan dash line. The algorithm is working quite reasonably. Here we'll assume that the data set is acquired appropriately. We'll not consider such a noise case. And once noise is involved, then the problem is way more complicated. So we'll consider good data only. Now that is rewriting of the definition. Okay, that is least square solution will have least norm square norm. Okay, we'll try to interpret this problem geometrically. Okay, let's see the figure and here. For all x in Rn, a and x, the product will be necessarily in column space of A. So we have to find an x. That makes ax the closest to B. Okay, let's see this figure. We have to find the x such that transformation by A, so that makes ax, that one must be closest to B, so that that is the least square solution. And now to get that one, and once we can project B onto the column space of A, and so that B hat is projection of B onto column space A, then this equation should have a solution because the projection is in the column space A. Now that should have a solution, and so that a solution X hat is on least square solution of AX equals B. So geometrically, we try to find the X hat so that AX hat is nearest to B. And also we may consider this one as the solution of AX equals the projection of B onto column space of A. Okay. The quantity B minus AX hat, the squared, is called the least squares error. And because now once X hat is found, then now this makes a vector, in fact that one, and each component makes error, and error each one is squared and added so that we can call it reasonably least squares error. But among every possible errors, and that is the minimum error, but we are measuring the error by using the square norm. So we have such a name, least squares error. A is a square metric and invertible, then AX equals B has a unique solution X hat, and therefore the norm of this difference must be 0. Right? Now, this theorem is saying a way of solving the least squares problem. A set of least squares solutions of AX equals B. The reason we are saying this way is that least squares solution may not be unique. So the set of solutions of this system coincides with the non-empty set of solutions of normal equations. So in order to find a least square solution of the system, we may try to solve this normal equation. Okay. Let's see the proof. It's worth considering the proof. We start with here assumption that X hat is now satisfying that equation, which means that X hat is on LS solution. Then here B minus B hat geometrically thereon, B minus B hat, that vertical vector, normal vector, that is same as now B minus AX hat, because B hat is same as that one. That is normal to column space of A. That means that now column space is generated by columns of A. So all columns, each column, the set of columns is a spanning set. So the vectors in spanning set and all vectors in the spanning set, the dot product is 0. Is orthogonal to column space A, means that for each vector in the spanning set, the dot product along with that must be 0. You already know that. Now, this dot product can be written as AJ transpose for all columns AJ. then for all columns AJ, then it's the same as that one, A transpose, rather than each column, so that is row eventually, rather than AJ transpose, we collect them, then there must be A transpose. Now, this equation can be written equivalently in this way. So we can conclude the theorem. Okay. So solutions of least scarce solutions of AX equal B are the same as solutions of these normal equations. Here we have A and B, a tall metric, and let's try to find least squares solution of AX equals B, and then we try to find the least squares error. Now, for this problem, we'll use the method of normal equations. Okay, so for part A, we try to get A transpose A. A transpose is 1, 2, minus 2, and 1, 0, 1. And A itself is 1, 2, minus 2, 1, 0, 1. Okay, so that'll make a 2 by 2 metric. Here, this dot product will be, okay, 1 plus 4 plus 4, that's 9. And now there's 1. Okay, we are picking only this one, that one, which means there's minus 1. Now, again, this product must be minus 1. After computation, it must be symmetric. So if you get this one, then again, the same value must be here. Now, this dot product must be 2. Okay. Now, how about A transpose and B? Okay, we have the same A transpose, and B is minus 4, 8, and 1. This row and column, so there is a minus 4. Okay, let's try to write down detail. Minus 4 plus 16. And here minus 2, so that will be 10. How about second one? Just add these two, so that minus 4 plus 1, which is minus 3. Right? So we have to solve the system with that 2 by 2 metric, and here right side is that one. And we can solve this one conveniently by using the elementary row positions and for the augmented metric, or you can find the inverse of that one quite easily. But anyway, we'll start with the augmented metric. Let's try to write down this one first. So the minus 1 and 2, and corresponding right side is minus 3, 9, minus 1, and here 10. Okay. From this one, multiply minus 1, 1 minus 2 and 3, and then 9 times addition will make 0. 9 times addition, okay, 18 is added, so that 17. Okay. Now 27 is subtracted, so that minus 27, or minus 17. Minus 27 plus 10 minus 17. Okay. So from here we have now 1, minus 2 and 3, and 0, 1, and minus 1. Okay, the second component of x must be minus 1, and twice addition. Then here 1, and twice addition will make 0. Twice addition will make 1, 0, 1, minus 1. Okay, so that's the solution. That's x hat. Okay. We got x hat on least squares solution. It is unique least squares solution. Now let's try to find least squares error. Okay. We go here. We'll write down here. Okay, this is space. Okay, B. And we have to get A x hat. Right? And then we have to make a subtraction from B. Okay. X hat is 1 and minus 1. 1 and minus 1 is multiplied. Then that will be 0. 1 and minus 1, that is 2. 1 and minus 1, that is minus 3. Okay. So B minus A x hat, that is now minus 4, and that is subtracted. So it is, we have a 6, and subtraction will make a 4. Okay. So here B minus A x hat norm squared. That is a summation of square of these entries. So that is a 16 plus a 36 plus again 16. So that is 68. Right? There is 32, 36. Okay, so 68. The theorem, the last theorem implies that the least square solutions of Ax equals B, the linear system, are solutions of the normal equations. But when this matrix is not invertible, then the normal equations have either no solution or infinitely many solutions. So to make it invertible, we have to get here good data. So data acquisition is very important, not to make the system so that one is singular. Once it is singular, then we have some problem. So data acquisition is, from data acquisition, we have to be careful. Here we have another theorem to saying the conditions for invertibility of the A transpose A, the matrix. A is an n by n matrix. The following statements are logically equivalent. The equation Ax equals B has a unique least square solution for every choice of a B. The columns of A are linearly independent, and the matrix A transpose A is invertible. So once the columns of A are linearly independent, then the normal matrix must be invertible and least square solution must be unique. So once it's invertible, then from this equation we try to apply inverse of that matrix so that x hat can be obtained through this equation. So the unique least square solution is obtained by that formula. We start with Ax equals B. Now, if A is not invertible or tall matrix, then A inverse doesn't exist. We cannot consider A inverse, but somehow it looks like A inverse, so that we call this portion the pseudo inverse of A, and that is often used in numerical analysis society. and also metric algebra. So you have to recognize the name pseudo inverse of a metric. Okay, that is pseudo inverse. Describe all least squares solutions of the equation ax equals b given in this way. Okay, now we'll use again the method of normal equations. First we make A transpose A. Now I guess the result is a 30 by 30 matrix, and always the result is in fact R, n by n. Right now n is 3, m is 4. Okay, this will be a 3 by 3 matrix. Rather than writing A transpose A, you may consider in this way. 1 position is dot product itself, so it is 4. And 1 position is first column, second column, dot product, that is 2. And 1, 3 will be this one, that one product, again 2. And that will be the same because it must be symmetric. Okay, 2, 2, that must be 2. Now 2, 3 must be 0, then it must be 0 again. Now 3, 3 is now 2. Okay. Okay. Now how about A transpose B? That is again, you may write down A transpose and then first row after transpose, that will be a first row and column, second row column, third row column. You can do that way, or just the first column, that dot product is the first entry, addition of that 4, and there's 10, so it is 14. Now second column, this the right side dot product will be 4, and the final entry must be addition of these two along with that dot product, there must be 10. So we have to solve this problem. Okay, here now for this one we start with augmented matrix. Okay, A, okay, just a moment, dot A. Let's start here, augmented matrix. For that one, and the right side, everything, every value even integers. So let's try to multiply half so that there's 2, 1, 1, right side is 7. There is 1, 1, 0, right side 4. Okay, oh yeah, must be 2. And now there is 1, 0, 1, right side 5. Right? Okay, from here we'll move this on the top 1, 0, 1, 5 and eliminate this one by subtracting here. So there's 1 and there will be minus 1 and subtraction makes minus 3 and twice the subtraction will make a 0 and okay, twice subtraction is not changing and twice subtraction there's minus 1, twice subtraction minus 3. Okay, essentially these two are the same, so that along with red color, once we subtract the second row from third row, everything will be 0. Right? Okay, we reach at the reduced echelon form. This is pivot x1, x2 are basic variables, and x3 is a single free variable. The first line is saying that x1 is the same as 5 times, okay, minus x3, and x2, second row, is saying there's minus 3 and plus x3, and x3 is a free variable. Okay, right here, x3. So from this one, the x is same as a constant vector is 5, minus 3, and 0. And along with here a free variable x3, the direction is minus 1, 1, and 1. Right? Okay. For any choice of x3, x will be solution. Okay, we say x hat. These are all solutions of least squares problem of that one with a and b given here. So for all choice of x3, these are solutions. Like that, sometimes least squares problem may have more than one solution. Of course, for every choice of this x hat, and if you try to measure ax minus b so that b minus ax hat, then that one will be always the same, because this portion will become 0. But anyway, a times this portion will be 0, so that this value must be always the same. And the value is minimum among all choices of x. Okay. Now for the least squares problems, we can get the solution by using skewer factorization. In the theorem, we'll assume that A is an n by n matrix with linearly independent columns, and A is QR. This one is QR factorization of A, as in a theorem in earlier section. Then for each B in Rm, the equation Ax equals B has a unique least square solution. Of course, even though you don't consider QR factorization, once A has linearly independent columns, then A transpose A is invertible. So the least square problem must have a unique solution. Now, but the unique solution can be written in this way. It's not really far away from the earlier theory. Okay, that comes from pseudo inverse of A. We define the pseudo inverse of A in this way. Now A is QR, and Q has property that Q transpose Q is identity. So that by using the property, we can simplify this pseudo inverse, and QR transpose QR, whole thing inverse, and QR transpose, and simplify. We reach that one. Just using this property, we try to get the pseudo inverse of A. Then we reach at this one. Okay. Now for this problem here, for your convenience, and QR is given. So try to find the least squares solution. It has unique least square solution, and first you apply Q transpose to B, and then apply inverse of R. Then you can get the unique least square solution. Just try it yourself. I believe I gave you here the answer. Okay. Okay, now we reach at the true or false problems. The general least squares problem is to find an x that makes ax as close as possible to B. Is it true? Yeah, it's true. When we consider geometric interpretation of the least squares problem, and we mentioned this one. So it is true. Any solution of A transpose A, x equals A transpose B, that is now normal equations, is least square solutions of AX equals B. Is it true? We mentioned in a theorem that the solutions, least square solutions of this linear system is the same as the solutions of this normal equation. So the statement is true. If x hat is a least square solution of the system, AX equals B, then x hat is now given in this way. Okay. Is it true? Maybe somebody may try to say it's true, but it is false. Now consider why it is false. Once it is unique least square solution, then it's okay. But once it is not invertible, then that kind of equation may have more than one solution. We considered one example here over there. Now A transpose A and A transpose B, we try to solve it. Now it has more than one solution, infinitely many solutions. So that A transpose A inverse, you cannot say this one because it's not invertible. It has only two pivots, so it is not invertible. So you cannot say this term. So impossible to mention this portion. So that statement is wrong. If you say the unique least square solution, then it is true. Or once you start from right side, if x hat is given in this way, then x hat is a least square solution of AX equals B, then again true. Either unique or the other direction, opposite direction, reverse, and then the statement must be true. But the current one is false. Okay, the final problem. The normal equations always provide a reliable method for computing least square solutions. Okay, it's too easy to say false, right? Not really always reliable. Once it is not invertible, then sometimes infinitely many solutions or no solutions. We didn't consider the examples. However, there are many cases that has no solution. Okay, that's the end of the section. Thank you.